if
Okay, so
if you want to take control of the PowerPoint, and then I'll just follow along with you.
well, did you send it to
No,
me?
no, I haven't.
Because
Shauna.
I can't scroll unless it's.
Okay, let me do that.
I
real
mean,
quick.
but unless you have questions about specific slides, did you?
No, Shauna, I think I just wanted you to kind of like glaze
Go
over it.
Sure.
Yeah, go
Well,
over
if
it.
you go back up to the first, couple of slides so we can see what's going on. So this is an example. So they're talking about vehicle quality surveys and customer satisfaction information. Using a sample of vehicle owners from recent vehicle purchase records, the survey asks the owners a variety of questions such as those that follow. For each question, state whether the data collected are categorical or quantitative and indicate the measurement scale. So remember, categorical is the same thing as qualitative with an L.
Okay.
And numerical and quantitative are the same. So you're using categorical and quantitative in your book. So categorical means that it's qualitative.
Okay.
And quantitative means that it's numerical. So it just depends on, okay, what price did you pay for the vehicle? Well, that's a quantitative variable, right? And it includes a 0 point because you could have gotten the vehicle for free. Maybe you got it from a friend. And so that I would say that that's probably on a ratio scale.
Okay.
The quantitative ratio scale. How did you pay? How did you pay for the vehicle? Cash, lease, or finance? Now here, this is a qualitative, right? And it's nominal. We can't judge cash as being better or lease or fine. There's no ranking to this, so it's just naming it. How likely would you be to recommend this vehicle to a friend? Now here, the ratings that you have, definitely not, probably will, definitely will. Those are naming, but they're also ranked. So your level of satisfaction is ranked. In other words, if you would probably recommend it, that's a better recommendation than if you definitely won't recommend it. But how much space is there between that? We don't know that. I could ask 10 people with the same 2 ratings, and those ratings might be a lot closer together or a lot further apart. I mean, some people, if they said definitely not, that would be like 10 out of 100, maybe, you know, where for other people, that's like anything below 50 is definitely not, you know what I mean? So it just depends on what they think. What is the current mileage? Okay, here again, it's quantitative. How far did we drive? What is the current mileage, right? Yeah. And in this case, are we looking at a
ratio or quantitative?
Yeah, because again, you could have something, I mean, it's not very common, but because you're going to have an odometer, but your odometer should start at 0. Right now, it probably doesn't because you drove it around the showroom or whatever, and it doesn't, but it started at 0. So it would be a ratio scale. What is your overall rating of your new vehicle? A 10-point scale ranging from 1 for unacceptable to 10. So again, now this is an ordinal scale, just like the C, right? But it's a 10-point scale. We don't have a true 0 here.
Okay.
We don't have a 0 that means absolutely not. So this isn't like, I would say it's more like an interval issue scale there. But it's an ordinal kind of variable. So sometimes these scales for like nominal and ordinal, they don't work very well because you can't put them on scales. You know what I mean? It doesn't scale the same way that a quantitative variable would.
What did we get for C? Ordinal and
The ordinal, and it's qualitative because it's a quality of something, right? So it's just a matter of okay, and here's just a review. This is summarizing data that's categorical and summarizing data that's quantitative. So these are some terms. Categorical data, okay, these are qualitative. Use labels or names. So categorical data are going to be on nominal scales. They could be on ordinal scales, right? Quantitative data are numerical. So they're going to be on a ratio or an interval scale.
Okay.
That's generally how it breaks down. That's why some of the exercise you were doing the other day was a little bit, I wasn't sure quite where she was going with a couple of those because it doesn't really fit in a strict sense. So here it's just, this is just a different, this is kind of some examples of where you would find statistics, different kinds of statistics that you would find. So customer satisfaction, cartons filled with, these are some things that you would look for or some things that you would ask about, but there's nothing to know on this slide. She's just trying to give you some, and then here again, this is a case of how are you going to organize the data? So I think the point that she's trying to get across here, and it's a good thing because I think a lot of students miss it, is sometimes students think, they read a question or they have data and they think it just arose spontaneously. Like the researcher woke up one day and wow, there was data, out popped the data right here. It doesn't work that way. People who study topics, you could study an accounting topic at Cal State Long Beach. I could study the number of people who come into the tutoring center, or the effects of sleep deprivation from being on Zoom, something like that. It always starts, like on the previous slide, with some sort of question or something that we want more information about. And we go and we gather data about that thing. Okay.
Okay.
And in this case, we have density data for the data that we were talking about. We have density data, so they gather it. But then what you have is this big, long, hairy list of data, kind of like our spreadsheet the other day, right?
Yeah.
And it's nice to be able to organize your data in different ways. So this top picture is a frequency distribution, right? It's a grouped frequency distribution. And the bottom picture below it is a histogram, or it's a histogram. So there's different situations that lend themselves to different kinds of graphing techniques that tell us different things. Okay, so summarizing categorical data. Here's what you would do. So these are the kinds of graphs that you would use for categorical data. These are things that are going to be measured on a nominal or an ordinal scale, usually. So you have a frequency distribution, a relative frequency distribution, which we saw in the homework. We did a lot of those. A percent frequency distribution. You have a bar chart, you have a pie chart. You can't use something like a histogram for that, because a histogram, you need quantitative variables on the x-axis. You need some kind of class width, and you won't have that. So it depends on what kind of data you have and what relationships you're interested in. Okay, we know what a frequency distribution is. It's a tabular summary of data and showing each of several non-overlapping categories. The objective is to provide insights about the data. So it basically, by summarizing the data and putting it in a picture, you can convey a lot more information a lot faster. And again, all you have to do to really understand this on an intuitive level is think about the data set that we were looking at the other day. Okay. Perfectly good data, credit card, proprietary information, all that, married, single, age group, all that stuff. Very hard to look at in its raw form like that and make any kind of definitive conclusions. Once you start putting together frequency distributions and you start drawing some bar graphs, you begin to be able to draw some conclusions about the data, because you start to see the data in summary. And then you start to say, oh, I can see a relationship between, for example, the amount that males spend versus the amount that females spend, or the amount, or the effect, or the presumed effect of the promotion versus the non-promotion, something like that. So just basic kinds of stuff, okay? So here they give you an example. I don't think we need to belabor this example. So here's guests staying at the Murata Inn were asked to rate the quality of their accommodations. Here's the data in the blue box. This is ordinal data, right? Categorical but ordinal scale, right? And they're gonna, now it's hard to look at this and see anything meaningful. I mean, you could start counting and doing some stuff, but once you start doing some analysis, you can start to see maybe what these people were thinking about. And so here's your frequency distribution. Now we can see from the distribution that about half the people had above average accommodations. So that's not too bad. That's a pretty good, that's, you know, I mean, it's not great, but that was by far our most, this is our mode right here.
Okay.
So that's a good sign. But you have, now consider this, you have just as many poor and below average ratings as you do average. So this is not a, like, this is not a super duper place. Like, you're not going to go and recommend this to everybody you know, but you could certainly do worse than this place, it looks like. So this might be, you know, out of 5 stars, this might be like a 2.5, 3 star. You know, this is not, but it's not go brag, but it's not like, please pass this on the highway. Like, I'm not even desperate enough to stay here at 3 o'clock in the morning with 1 gallon of gas, you know, like.
Right. Okay.
So it gives you some idea. And then we do the same thing with, now you were asking me about like the formulas and how we do it, right?
Yeah.
This is a statement of the formula, okay? It doesn't give you the formula like as a mathematical formula, but it tells you what it is. The relative frequency of a class, so of a group, like the below average or the average or whatever, is the fraction or the proportion of the total number of data. So that would be 20 in our last example, belonging to that class. So if you go back to the last example for a minute, if I want the, like, let's say I want the relative frequency of the poor rating, right?
Okay.
I'm gonna take this number that's in my category 2 divided by 20.
That's 10%.
And that would be 0.10 for my relative frequency. And then my percentage would be 10%.
Okay.
That's all that means. Relative frequency means your frequency when considered with the, against the total. Okay. And then we get that frequency distribution. So now here, the difference here, because we were doing this yesterday, remember, we had this in the homework, the percent frequency is where you take the decimal, which was 2 out of 20, which was 0.10, and you multiply that by 100 to get the percentage. Okay, so the relative, so this book is making a distinction. It's a distinction, but it's a small distinction. This is a really small distinction. This book seems to make that distinction, so just be aware of the wording.
Okay.
Relative frequency is going to be the number of observations in the class or the category divided by the total, and you're going to express that as a decimal. The percent frequency, you're going to take that same calculation, the number of observations in a category, divided by the total, and then multiply by 100 and use percentage.
We're always multiplying by 100, Shauna.
Mm-hmm.
Okay.
Because percentages are out of 100. The way that we change a decimal to a percent is we multiply by 100. Right? So that's where the 100 is coming from.
Okay.
So here they give you the, now, see this is, because it doesn't have the original amounts, what it's doing here is it's doing this. It's saying this would be more explanatory if, so like for poor, you have 2 is the count, right? You had 2 observations out of 20. Right? So
Right.
that gave you, that was your fraction, 2 out of 20, right? So your relative frequency was 0.10. This is your relative. I'm going to move it up so that we can see. So here, this is 2 out of 20. This is 0.10. And that's where this 0.10 is coming from. That's this 0.10 here. Let me put the arrow next to it. That's this 0.10. Anytime you take relative frequency, so the percent frequency is always the relative frequency times 100. And the reason that it's always 100, again, is because that we're converting the relative frequency times 100 is because we're converting a decimal to a fraction when we do it. That's why. Okay? But that's how it's coming out. Okay? Is that clear? Clyde, are you with me? Oop. And so the percent frequency is going to always be the relative frequency. Oops. It's going to be the relative frequency times 100, and that's because we're converting it to a whole number, a percentage. This is a percent. This is 10%. So these could all have percent signs, 10%, 15%, and so forth. You with me, Clyde? You look frozen. Your I can't hear you. Oops.
Share my screen.
Okay, so then we get to the different types of charts. This is just giving you characteristics of the different types of charts. So a bar chart, the biggest thing here is it's a graphical display for depicting qualitative data, okay? So you have to have qualitative data in using a bar chart, okay? And then it tells you which information goes on which axis. Okay, so this is pretty self-explanatory if you know what a bar chart is, and we've done enough of these to know, but the biggest thing is it's qualitative data. So here you have the ratings at the bottom, and then you have the frequency, okay? So that's pretty much a bar chart. A pie chart, we were doing this the other day. You can use relative frequency, again, categorical data. That's important, okay? These displays, bar charts and pie charts, are for categorical or qualitative data. That's one of the reasons why there's such a big emphasis on knowing what the types of data are, because some of these chart types are only appropriate for certain types of data. Okay. Then it gives you a little bit of information about how to do it, draw it, figure out how many degrees there are. So that's just kind of how that works. And here's an example of a pie chart. Okay, so then here's more information about the bar chart. And then here again, now we're switching gears. Now
Okay.
this is quantitative data, quantitative. So now we've got more choices for how to summarize it. Again, we have the frequency distribution. We have a relative frequency and percent. So those two are applicable for both. But then when you're doing quantitative data, you can use a dot plot, a histogram, some sort of cumulative distribution, or a stem and leaf display. So this is just kind of breaking it down for you, which types. And then you go through. So there's an example, another one, Hudson Auto Repair, okay? The manager of Hudson Auto Repair would like to gain a better understanding of the cost of parts used in the engine tune-ups performed in the shop. She examines 50 customer invoices for tune-ups. The cost of parts rounded to the nearest dollar are listed. So she gives you the data right here. There's the data. It's very hard to kind of get any sense of what this data is. So she's going to summarize it somehow. Okay. And here, this is how you create a frequency distribution. So how many classes do you want? And how wide are they? And what are the limits? Okay. So then you have some rules. 5 and 20 classes, data sets with a larger number of elements, smaller data sets would do, okay. So now this is a different little rule. This is a rule that I haven't seen before. Scroll up just a bit so I can see the, all right, this is the rule they seem to be using in terms of number of classes. A useful recipe to determine the number of classes, K, is the 2 to the K rule, such that 2 to the K is greater than N, where N is the number of data. So it's kind of interesting because in every other book that I've seen, except for one teacher who's taught this, they usually tell you how many classes they want. or it's an arbitrary sort of decision, somewhere between 5 and 20. This is usually not something that we consider. But here they're saying what you can do to figure out what K should be, how many classes do we want, is figure out how many data you have, okay? So if you look, go back and look at the Hudson example for a minute. How many data do we have here? So there's 50 tune-ups. So what we would do is we would want to take 2 to some power and get as close as be greater than n. So 2 to the first is 2, 2 to the second is 4, 2 to the third is 8, 2 to the fourth is 16, 2 to the fifth is 32, 2 to the sixth is 64. So 2 to the sixth being 64 would be greater than my number of data. So I might choose to have 6 classes here. Because K, I mean, it's not, if I have 5, nobody's going to kill me. But I might choose to have 6 based on this rule. Let's see what she comes up with. So scroll down past that and let's see how many classes she decides to use. Okay, so use classes of equal width, get the number of classes. Okay, which one? Okay, keep going. I'll come back to the largest, smallest in a second. Yeah, this is just what I was telling you, okay? So here there were 50 data. N is equal to 50. If we try K equals 5, 2 to the 5th is 32, somewhat less than 50, hence 5 is not enough. If we let K equal 6, then 2 to the 6th is 64. So the recommended number of classes is 6. Now, that's from her 2 to the K rule. Do you understand where that came from?
Yes, yes, Shauna.
Now after that, all you're doing is, all you're doing here is what we've typically done in, I think, most of your other classes. So your class width, is going to be right. It's going to be this formula here. It's going to be, and I usually write it as class width is equal to the range, because large data minus small data is the range. Range divided by the number of classes. That's usually how I think about writing it. So range divided by the number of classes is your class width. So she's going to take the high minus the low and divide by 6. Okay, keep going. So we keep going. So she did that now. 9.5. We can't have a class width of 9.5. Go back. So what she's going to do is she's going to take this up. She's going to take this up. Now, it depends on the book. This is one of those cases where different books teach this different ways, okay? And so sometimes, and I feel for you with taking different classes, because even if you go and ask my teacher, right? She has a different preference on some of it. She'll want to make her class widths odd. So she would make this not 10, she would make it 11, and there's a reason for that. But here, what your teacher seems to be doing is rounding to the nearest whole number, okay? In any case, regardless of what kind of rule you're using, it has to be a whole number. Your width is not going to be some kind of decimal. Not usually, I mean, unless your teacher tells you different, but usually class width is a whole number. Okay. So then she does her distribution. Now she skipped a little bit of this, okay? Because what we would have to do now is either put the data in a spreadsheet or in a calculator, rank the data, right? And then we would have to see, okay, if we start at 50, okay? Now this is another this is another thing that happens that's different in textbooks, okay? So different textbooks will tell you differently. Some books will say, start with the lowest one, which is 50, right? Some books will say, go ahead and start 1 or 2 units below that, so that you can make the width balance, okay? So it just depends. But here they're starting with the lowest. So remember, our class width is 10. Now, very important here, because this is a problem for people. When you do this thing, okay, this class, this what we call this lower limit right here, okay, this lower limit being 50, the width is from the lower limit to the lower limit. So notice that this is 10 units, okay, not over here. So 60 doesn't go here.
50 to 60, okay.
It's to the next lower limit. So when you're doing it, the class width, which is 10, is from the lower limits. So from 60 to 70, from 70 to 80, and so on. And the same thing. Now, here, you don't want these to overlap. You don't want these class. So what you do is, one of the ways that you can look at this, if you've done your lower limits correctly, okay, so you just add 10, 50 plus 10, 60, 60 plus 10, 70, 70 plus 10, 80, and so forth, right? Is to figure out where this upper limit should be, the one that I underlined right here.
Mm-hmm.
You take 1 off. So if this is 60, this is 59. See, this is 70, so take 1 off, you get 69. Take 1 off of 80, you get 79. And they will also be 10 units apart. So 59 plus 10, 69. 69 plus 10, 79. This difference is your class width that you found in the previous step. So this limit, I'm sorry, this width is going to be 10 units. 10, and then there's going to be another 10 down here, and so forth. 10, 10, and these are 10 also. And so it's going to be consistent with whatever the width is supposed to be.
Okay.
Okay. So let me erase this and we can move on. Okay, so then guidelines for determining the class limits. Class limits must be chosen so that you have only one and only one. In other words, you can't have a value in your data that could belong to 2 classes. If you remember when I was doing the chart yesterday, that's why I had to change the labels, because I can't have 2 places for one value to go. I have to have a single class to which each data value would belong. Okay.
Okay.
So there's those rules. Most of those are common sense. Most of those are common sense, and I don't think that will be a problem for you, but those are part of the book, so there might be a question on the exam about the appropriate rules for that. Any questions about any of those rules?
No, I think I'm good so far, Sean.
Okay.
Thank you.
All right. So then she created the same thing. Okay. So we did the same thing here. Remember, there were 50 values.
Mhm.
So when she counted, there were 2 values in this class. Now, you have to look back at the frequency, but you'd be 2 out of 50 and then so forth. Okay. So, okay, then you go back and now here it's just insights related to that particular example. Okay. So not too many people, or not too many parts, I should say, are between 50 and 59, right? So most of them are within 70 to 79. Okay, so then, okay, now we're going to go to a dot plot of the same data. Okay, so here you're going to, she just did 50. This is 55, 60, 65, 70. And each of these dots, each of these light blue dots on this blue background is a data point. Okay, so what she's plotting here is the original data. She's not plotting from the frequency distribution. She's plotting the original data values on her dot plot. Okay, and then again, she just gives you some data. I mean, some descriptions. Okay, then we're going to go with a histogram. Okay, so it's these are the ones that have rectangles that touch each other. These are kind of like bar graphs, okay, except that the bars usually touch each other unless you have a class where there are no values. They touch each other, and their histograms are for quantitative data. Bar charts are for qualitative data. Okay. Histograms are for quantitative numerical data, and bar charts are for categorical qualitative data. Okay, and I think it says that on the next bullet point, go down to the last bullet point. Unlike a bar graph, a histogram has no natural separation. So yeah, you don't generally separate that. Okay, so then she shows you a histogram. There it is. Now, just to kind of help you with this, let's go back for a second. Go back one. If you look at this slide here, before we talk about skew, right? When you talk about distributions, we talk about 3 characteristics. We talk about more, but we talk about 3 characteristics. We talk about the shape, we talk about the center, and we talk about the spread. Shape, center, and spread. So shape we can describe in different ways, but typically when we're going to describe shape, we talk about shape can refer to things like it could be normal. Sometimes we talk about this as being symmetric. So it could be normal, symmetric. It could be left skewed. It could be right skewed. It could be uniform, rectangular. So there's different words to describe shape. In this case, this is a little bit skewed to the right. It's a little bit skewed positively because your hump is on the left. Your mean is not quite in the middle here. It's a little bit skewed. If I had a hump that was if I had a big tall bar on the right, say where 90 to 99 is, then it might be a little bit left skewed. It might skew to the left. Okay.
Skewed means that's where the less of the data is at.
Okay, so that's a good question. Let me show you something here. So when we're talking about, I'm gonna share the whiteboard for a second. When we talk about skew, because students always have a question about how to name it. So you have your bar, right? And then you have, let's do this. So if we're talking about symmetric, that's something like this, right? That's symmetrical. If we're talking about skewed, then we might be talking about something like this, where have your bar, right? And then you have, here's the big hump, right? The big hump, and then it falls way down like this. So in this case, my hump isn't in the middle of my distribution, is it?
No.
Now, you think about where your tail is at, okay? This is and this is what's counterintuitive for students. A lot of times they're like, well, I don't know what to do. So this is a left skewed distribution, or a negatively skewed distribution. So it's, the skew is in the direction of the tail, okay? And the hump, so the hump is where the mode is located. The hump is where the mode is located, and the tail is the direction of the skew. So if you had a situation where you were talking about, let's say I drew this picture. Here's I draw my hump and it's way down here. This is a right skewed hump, because here my tail is on the right. My mode is low, right? But I have a lot of people that got low scores, is what this is saying. Most of my people got low scores here, right? That's my mode. But I have people that got really high scores, and so it's pulling the mode, pulling the median with it, right? So this is going to be a right skewed. This is going to be right skewed. So you look in the direction of the tail.
Okay.
To find the direction of skew.
Thank you, Shauna.
Look up, find the big hump, and look for the tail.
Okay.
Okay.
Got it.
All right. What you got for me? Go ahead and share your screen again.
Okay.
And I think the next thing she's going to do is show you that on the next screen. Now this one is nice and symmetrical, right?
Left skewed, the tail's down here. Right skewed.
Yeah.
And this is right skewed.
Yeah, that's more right skewed, right? And then we do cumulative frequency distributions, cumulative relative, and cumulative percent. The only difference here is that instead of using the frequencies of each class, we're using the cumulative frequencies, the cumulative distributions of each one. But the math is the same once you accumulate the numbers.
Okay.
So here's how it works, okay? Because the only thing here, and I don't know that you and I have gone over this yet, but it's very basic. So here we talk about it's probably better to go to the see, it would be easier for you if she go back up to the frequency distribution for Hudson Auto, which is probably like 10 slides ago, something like that. It would probably be easier for you to see it from that data if she did one. Okay, yeah, this will be fine. Relative frequency, we know there were 50 data, right?
Yes.
So I'm going to do something here. So this is 50 data. So I'm going to make the, let me see. It would have been easier if she had done another one. But if I just do the frequency, right?
Right.
If I just do the frequency, that's how many data values there are, right? Well, there are 2 here, right? There are 2, and I know that because she did 2 out of 50, right? Now, this is 26%, so this is going to be 13. There's 13. And if you take 13 out of 50, you'll find that that's 26%. If this is 32, this is going to be 16. There were 16 values in here. Now, I'm doing it by sort of doing the math backwards. What she did was she counted. She tallied these. So there were 16 data values from 70 to 79. So there were 16, let me erase this. There were 16 data values from there. And here, so there were 16 data values here. The 16 text box. Let me see if I can type. Is it gonna let me? It's not gonna. Hold on. Let me see. 16. It's not letting me type in there, so I'm gonna have to. But there are 16. There are 16 here. $16 out of 50 is 32%. There's 7 in each of these. There are 7 in both of those. And then there's a 5 in the last category.
Yep.
So if you add all those up, you should get a total of 50 values. 6 plus 2 plus 13 plus 16 plus 7 plus 7 plus 5. Okay.
Okay.
Now, cumulative frequency means that you're accumulating the frequencies. So you always get your first cumulative frequency for free. It matches your frequency. So that's 2. Okay. Now, the way that you get your next cumulative frequency is you take this 2 right here and you add the frequency below it. So 2 plus 13, that'll give you 15. 15. And then you take 15 and you add 16. 15 plus 16 is 31. 31. Then you add 31 to the next frequency below you. 31 plus 7 is 38. 38. You take 38. Then you take 38 and 7, and you get 45. And 45 plus 5 is 50. That's your cumulative frequency, okay? What she's doing on that slide that we're looking at is she's taking these numbers here. She's taking these numbers that I just got in the cumulative frequency column. Remember, there's a 45, and then there's a 50, right? The last cumulative frequency, by the way, should match the total number of frequencies there are. So what she's doing in the slide that we're looking at is she's taking these cumulative frequencies and she's making them into relative and percent. So she's taking 2 out of 50, which is 0.04, which is 4%. But then the next category is going to be 15. 15 out of 50 is going to give you a different decimal. So let's scroll down to where you were at with your, okay, go back. Okay, so here, this is my numbers, 2, 15, 31, you see it? She didn't do this part for you. But you have to do that part to get, you have to do that part to get the numbers that I got right here. 2, 15, 31, 38, 45. So that's where she got those from, okay? Now where she's getting the other numbers from is she's doing the same exact thing she did before. So remember, you have 50 still, right? So she's taking the cumulative frequency of the class and dividing it by the total. 2 divided by 50, 0.04.
Right.
15 divided by 50, 0.30. 31 divided by 50, 0.62. Okay. 45 divided by 50, 0.90. And 50 divided by 50 is 1. Okay. Now notice here that when you do the cumulative relative frequency, it's more than 1. Okay, which is fine. The sum is more than 1. And then the percent frequency is just this decimal multiplied by 100. But that's the difference between using the frequency and the cumulative relative frequency. So it's just the same mechanics with different numbers.
She skipped the step that you showed me, Shauna, where how she got the 13, right?
Right, because what she did was she didn't give you the frequencies anywhere. which is why I put them in there. Okay. And I fudged it based on her numbers here. But what she did to get those numbers, if you go back to the original data, go back to the blue data box. Okay, go back to the data for, okay, stop. So here's your data, right? What she's doing is, remember her classes are 50 to 59, right?
Mhm.
So how many numbers in the box are between 50 and 59?
Oh, I see.
Well, there's one here
52 and 57.
and there's, where's 52?
Right next to it on the right.
Uh,
You're a number over. on
I
the
see
right.
70. Oh, there, right
Mhm.
here. So there's two of them,
Okay.
right? Now, if I do 60 to 69,
That's
how
what
many
it's
of
at,
those are
13.
there? So there's 1,
2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12,
there should be one more.
13.
13, right? That's where she's getting it from.
Okay. Okay.
So those, yeah, she should have shown you the original
She should have cleared that up.
frequency
Yeah.
distribution. That would have been easier. Okay.
Mhm.
Does that make sense where it's coming from?
Yeah, Shauna, thank you for that.
You're welcome. But yeah, that she kind of left that out. So let me erase this part.
The stem
Now
and leaf, I
here,
remember.
huh?
I remember when you showed me the stem and leaf before.
Right now here, all we're doing is, put this in a calculator or on the spreadsheet, and we're doing from 50, 60, 70, 80, 90. This is 100. So you're doing 52 and 57. This is each individual data. So 62, 62, 62, 62, 65, 66, 67, 68, 68, 69, 69, 69, and so forth. Okay. Okay. Now here, sometimes what you have to do is you have too many values. So what they do is they stretch it out. Okay. And so what they might do is they might say, well, we're going to make 50 to 54. We're going to make that the first stem, right? So notice here that we had 52 once, right? And that went on the first 5. Then the second 5 is really the numbers between 55 and 59. So this was 57, right? It's easier to see in the 60s. This first 6 is from this, the leaves are going to go from 0 to 4. So you're going to have 62 occurred 4 times. And then the numbers 65 to 69 occurred this many times.
How do we determine the leaves again, Shauna?
By the number. So you go back to the data.
Uh-huh.
You go back to the data here. Like if I was going to put this 69 here would be 6 on the left and 9 on the right. So normally in a 2-digit number, your left digit is the stem and your right digit is the leaf.
Okay. So here on this one, I noticed that they went 52 and then they went all the way to 57.
Because
so
in this case, what they did is they stretched it out. That's what I was explaining. So instead of having classes that were 50 to 59, essentially what you're looking at here is 50, this is 50 to 54.
Okay.
So anything that's, it would be 50 to 54, you didn't have any data that was bigger than 52, but this would have been 50 to 54. This second one would have been 55 to 59.
59, I see.
This would have been 55 to 59. And it's easier to see in the 60s because the 60s had that data. So the 60s, the first one was 60 to 64. So you only had a bunch of 62s. But notice on the second 6 right here, you have 65, 66, 67, 68 occurs 3 times, and 69 occurs 3 times. It's a way of stretching out the data so that you can see it better. So then there's a few rules about the leaves. This is a question that you just asked me. So this is the rules about the leaf. So a single digit is used to define each leaf. The leaves are the ones on the right. In the preceding example, the leaf unit was one digit, okay? Leaf digits may be hundreds, tens, 0.1, and so on. So the leaf can be a decimal number. The leaf could be 2 digits, whatever you want, okay? Where the leaf unit is not shown, it's assumed to equal 1. So then she gives you another example. Go ahead. Here she gives you a smaller data set with an example, you see? So here, this is 8.6, so you have 8, 6, 8.8, 9.1, 9.4, you see?
Yes.
Now here's another one where we do it with 10 units. We do it with 10 units. So here we have, this is a 4-digit number, right? So what they decided to do here was they took the first two, like 1800, 1700, 1900, and so forth, right? And then they said 16, so 16 and 8. So when they had 16, it was 16, 8. And so this is, they rounded it down, which that I've never seen. That I've never seen that particular convention. This is the first textbook I've seen that does that. I've never
So
seen.
they rounded both of them down.
Yeah, they what they did is they rounded all of these units to the 10th. So this would have been 1810. So 1806 would have been, so this would have been rounded to, this would have been rounded to 1810. And then 1717 would have rounded to 1720. Or maybe down to 10, I don't know. But because it looks like they, yeah, I've not seen that before. Not seen that, but okay, then you have the data set, okay. So frequency, bar chart for categorical data. This is your Excel steps.
That's Excel steps, okay. I think that's it, Shauna. The rest are Excel steps.
And then what else you got? Only that?
Yeah, this lecture is done.
Okay.
Maybe next time we can do the other lecture, Shauna.
Yeah, if you want. How was the rest of the homework and everything? It went okay?
Yeah, Shauna, thank you for that. I appreciate your help.
I'm sorry that we messed up those 3 counts, but
no.
I don't think it was too bad.
Not at all, Shauna. Thank you.
Are you gonna have a chance to talk to her before?
I'm gonna speak to her tomorrow, yes.
Yeah, just let her and find out like how she wants you to handle the upload.
Okay.
Because if you need help doing the upload, I work tomorrow from 12 to like 5, I think it's 5. But I'm free in the morning. They're coming to do a COVID test in the morning, but otherwise Otherwise I should be free. So if you wanna